All right, the recording started. I'm using Panopto. This is the first time I'm trying Panopto. I didn't try it before. Hopefully, it's gonna work. Um, okay, just to give you some update. Actually, it's not a good news for your side. Is I can't share the lecture, the OneNote, as like any other classes I used to do. Not only me, no one can do that anymore. There's the federal rules now. Means I can only share the digital version. If I have something written, handwritten, I can share it with the students. But you know, it will be still the same. I'm gonna give the lectures in OneNote, and you're gonna take the class notes. Okay. Unfortunately, like before, you had the access of everything during the exam. You don't have it anymore. Yes.
Um, so we still have access to the OneNote from Thermo. Will you leave that up? Because I've been using that a lot.
Yeah, technically, I don't have to do anything now
Okay.
on that one. So yeah, that is still. I mean, you can download it and do something about it. I don't know when the access is gonna go away.
Okay. I've been using that a lot for my cat. So.
Yeah.
We don't have access to one.
Yeah, it's really hard news. I know for you guys. It's not only me. There are like around 8 faculties or even more use this thing. Okay, and none of us can do it anymore. The only way we can do it is give you the printout. Okay, so you know digitally. I mean, I can't share anything digitally where I have handwriting.
Oh,
It needs to be typed.
because the new
Yeah,
accessibility stuff.
Yeah, I don't understand it further, but that's the federal rules. That's how I should put it, right? So there's nothing I can do. Okay, nobody can do. Okay, so what could be the way around, right? Is still we need to get the materials out, right? So I choose to use the bright space. Still, I can't upload whatever handwriting thing will happen here, but on bright space, this course is. I remember I was saying like great organizing guys have all the PPT, all those things, right? PowerPoint presentations and everything, like the class materials, practice problems, homeworks, all those things, right? Like anything in the PowerPoint or the practice problem or whatever I was saying will be in the bright space for you to access. I'm going to show it to you shortly where those are located, how to use them, all sorts of things, right? Um, okay, appendix, the same thing I can do. I can upload it in bright space, okay? But at any case, I can't give you the access of this one, okay? But the one that will be here, whenever I will be using, you can take notes. And if you miss class for excused absence or for whatever reason you come talk with me in person, then I can actually give you a printout. You know what I'm saying? Of that class notes if you miss a class. It makes sense? But other than that, if you're gonna come to the class and you take the notes, it should be good. Is it clear? Any question?
So you're not allowed to share the OneNote with us?
I'm sorry.
No, you're okay. It's not your fault. I was just curious about how.
Yeah, not only me, other faculties are disappointed as well. But that's the rules.
Mr. Haskins had to remove some of his stuff for the same change that the school made. There was a bunch of stuff he's not allowed to show either. It's like accessibility stuff.
But like, if he has a video of him explaining it.
Oh yeah, I can upload the video. That's what I'm doing now in Panopto. So Panopto is part of Brightspace. I already pushed the recording button. I didn't do it before. I don't know how well it will be. But again, I have multiple pane involved to put it ready for you. Just to tell you what I gotta do. Once the Panopto is done recording, then I have to do it like closed caption first of all, and then I have to upload it and convert it to MP4, and then I have to upload it in YouTube, and then I can only give you the link of the YouTube. So it's the multiple pane over there. You still are gonna do that, but you can see it in that way. Yeah.
Could you email us a link to the OneNote?
No.
Really?
It sucks. I mean, if you are not my student, if after the class is done, you are no longer registered, then one-to-one setting, I can obviously share with you everything. That's a different thing though.
Yeah.
But not in class. In class, yeah.
Fair enough.
Yeah. In person, anything can happen, but formally, with the class registration and everything, I don't think anything can happen. All right, so let's just move on. And I'm hoping the recording is on. As I said, I never did the up to recording. If the recording for today's class doesn't go through properly, I'll soon talk with them, like whoever is involved on this, so they can help me to get the recording properly. Okay. It says Panaptu is sharing your screen. Okay, so hopefully it is on record now. So I was just talking about. Okay, I was just talking about. Sorry. Okay, now I found it. That where you can find the materials, right? Yep. So I gotta go here. Here, content. This is our Brightspace page, right? So this course goes by module. I have 8 modules to cover for the semester, right? We are in first module today, which is basically the intro stuff. Okay, let me show you what I have in module 1 here. Okay, so I do have like module 2 also filled out. Module 3 I started to fill out materials here, but let's just show you module 1. So in module 1, when you're going to go here, it does have one time I teach this course as online as well. Okay, so it has much more formal approach, as you can see here, like what needs to be read, and much more detail, right? So those are the things I'll not gonna spend time, waste my time here in class time just to explain those. Just to give you highlights here. Here you'd be seeing like what to read, where to read, what assignments you need to do, those sort of thing, right? The summary of this module, that what you'd be doing, something like that, which you would be learning soon on the material, actual material itself. Okay, after that you are seeing the reading resource, right? And the reading resource, the thing that I would be showing it to shortly, it's a PowerPoint. Okay, now it's not like I'll just go PowerPoint slide by slide. I use the OneNote, so I'm gonna put the notes next to the PowerPoints when I'm explaining those theory. Okay, it makes sense. Would be sticking with theory quite some time before we really jump into the math. Okay, initially. Okay, after a good grasp on it, then we're gonna do that. Then there's this assignment, means the homework number 1. I initially put the date like on next week Thursday. I don't know if we can meet that, but just the optimistic goal I have now, weekly assignments. Okay, I do have 8 to 10 assignments, as I said before, right? So it doesn't need to be weekly every time. There are some materials which will require more than a week of understanding to even deal with this homework. Okay, and finally, there is this practice problem for this particular module. So what are these problems? Actually, I got it from the book, exercise problems, not the examples problem. So I just pick up some of the problems which I feel like maybe you should be practicing more. I mean, I can show it to you later, obviously, but just to give you a highlight here, what you would be seeing on over there is a problem and the answer with the detailed explanation on it. Okay, that means as the whole solutions are there, you don't want to look at the solution, rather you'd like to try to solve it by yourself. If you struggle or whatever, then you look for the solution. Okay, at least bare minimum you review it. Okay, if you don't have time or whatever. Any questions so far? All right, now the actual materials, right? So there's the Brightspace. The actual material is obviously here. And today's topic is part of module 1, which has all those things are in the Brightspace as well. Means this PowerPoint, this text, whatever you are seeing here. Let's just start with this chapter 1. Okay, now chapter 1, when I'm saying chapter 1 is for Sangel. Chapter 1 is for Incropera. I mean, as I said, like either book, the classical one does have the same content what you are seeing it here. Okay, so without further ado, let's just start. What is heat transfer? What do you understand by heat transfer? So heat is energy, and transfer means when energy get transferred. And it can only transfer when there is a change of temperature, right? I gave you the example last day. If you have if you are just sitting here, you are constantly radiating heat, right? Because you have high temperature, simply more than the air temperature. You know that, right? You have 98, air has 70, 75, 80, whatever it is, but it's much lower than your temperature. So you are constantly radiating, means the heat transfer is happening here. Okay, so assume in a hot oven, right? Inside the oven, so there are two cake that you are baking. Okay, so from cake one to cake two, are you expecting heat transfer happening? It could be, if there is a temperature change between those two cakes, right? Does it make sense? But if those two cakes are in at same temperature, then there won't be any temperature exchange happen. Sorry, heat exchange happen from one cake to another cake. Okay, so bottom line, anytime you're seeing a change of temperature, there is a heat transfer. Is it clear to everyone? Heat transfer means difference temperature. Okay, if there is a difference in temperature, there is a heat transfer that is happening. Okay, done. And as I said, I'm going to try to use the black color only. Okay, just for this. What is the thermal energy? Okay, thermal energy associated with the molecules, right? If the molecules are moving faster, then we'll be expecting higher temperature. If it is moving less of speed, then the lower temperature. So that's simply put it this way. Think you are boiling water. Initially, I mean, even in visual, molecule you can see, you know that, right? Even in visual, like initially you see nothing happening in a pot, some cold water is sitting, right? A little bit. Okay. And then you are hitting the water, right? What will happen? You're seeing something is moving. Means a particle molecular movement is there, but microscopic molecular movement is always there, right? So bottom line, more the movement, more the heat energy. Does it make sense? More the thermal energy, okay? And how molecules can move? It can move like if it's depending on the media, right? If it's like a fluid, means air, water, you name it, right? On those, the molecular movement are much faster. If it is a solid, molecular movements are much strict. You know what I'm saying? How does molecule transfer the heat that in solid? You know, by vibration, right? In air or in water, means like in fluid, it has more of a movement, like translation and other movement within time, right? You might have learned this in physics class before, right? In high school. Okay, so that's the thermal energy. Moving on. Any question? I'll be soon started writing. Okay, not yet. Let me get my class notes. Sorry. All right, I got my class note. So the next thing is some of the parameter that you would be using all the time. Okay, let's see how much you remember. Let's start with the temperature. You guys remember the units of temperature? Degree Celsius, degree Fahrenheit. Any other units you know? Kelvin, Rankine and Kelvins are absolute temperature. Remember there are relationship between them with the regular temperature. Just to give you a quick review. So you see, degree Celsius plus 273 gives you Kelvin, right? Degree Fahrenheit plus 460, right? Gives you Rankine. Remember those? Okay. So we'll be using SI system, right? This is SI all the time. Time to time, we'll be using English unit as well, right? English unit. Sometimes they name it as inch pound. Okay, IPS as well, right? Inch pound second. So there are different names out there. US customary unit. Sometimes they say that, right? All right. So let's just move on to other things. That's the temperature. Obviously, the thermal energy. Okay, I did the mistake again. The black color only. So the thermal energy. The energy has a unit of joule, right? So you're seeing it joule or joule per kg, right? It already remember from thermo class when we have per unit kg, that refers to what kind of property? Specific. Specific, right? Like specific internal energy, specific enthalpy, specific, you remember those properties? Specific entropy, right? Ring a bell? Specific volume. Those are the main four property we learned. Every time we had a specific property, that means per unit mass or kg. Is it clear, everyone? So that's why joule or joule per kg. All right. Heat transfer. What is the unit of that? Anyone? Okay, so heat transfer is joules per second. Actually, they have it written as heat rate, which is watt. So watt or joule per second. Now, oftentimes you'd be seeing they use the unit as kilowatt, right? Megawatt, depending on how big is that. Kilo means 1,000, and mega means 1 million, right? You know that. 1 million watt equal to 1 megawatt. So the joule is the unit for heat. Okay, so just to give you a highlight, so you see, heat rate is per unit time. When you have, remember in thermo, everybody took thermo, right? Everybody. Okay, so when you have in thermo, the rate equation, then you had what? When you had like time multiplied with the rate equation, then you had it in joule. Remember that we did it like when you have rate equation, we had like dot on the top of every term, right? When we don't have a dot. But interestingly, in heat transfer, since it's like rate everywhere, right? So you'd be seeing the Q, that symbol that we use for heat rate, doesn't have any dot. Okay, but it has dot. You understand what I'm saying? It is for what? Because this is what the book use, like all heat transfer book use. They don't use the dot. Usually they use a small q for that, right? That's the symbol they use. But remember, in thermoclass heat rate, we use capital Q dot. Okay, just to give you a heads up at the beginning. Okay, this would be something you'd be seeing in the book all the time. Heat flux, very, very important property. Heat flux. Why is it important? Let me give you some intro first. We know the heat rate for the whole side of the world. I mean, this is not a good example. This side of the world, right? Outside, snowing, temperature is freezing, right? Less than 32 for sure. I don't know, maybe 20 or 15, whatever. Inside 70, right? Obviously, heat transfer is happening inside top side, right? Obvious, right? So now that heat transfer, when I said it's happening in watt. We know that, right? Heat rate, and that's for the whole wall, whatever amount of wattage that we are losing. Why that watt is important? You're heating this room, right? Right, by air conditioning. So you need to know how much you're losing, so you can provide that in wattage, right? You understand that? Now, say like we're interested to buy a window. Now a window, not that many window, and a window doesn't care how many windows in this room. A window doesn't care how many windows in this whole building. Does it make sense? So then you'd be interested to know, not for this particular room, how much of the heat that we're losing for this window, rather how much of the heat we're losing per unit area of that window. Does it make sense? So the per unit area is the keyword here. So when you're dealing with per unit area, that's the heat flux. Does it make sense? So heat flux is the unit property, okay? Per unit, whatever. In this case, it's per unit area. So very important property. What is the unit? You might have already have an idea, right? Watt per meter square, right? Heat flux meter square is the unit of the area, per unit area. So let me highlight that. So that's very important. So if I'm gonna give you a quiz, say like next week with those fundamentals, you should be able to deal with that, right? What I'm saying, as long as you do a review. As long as you do a review, you should be good on that. Okay, moving on. So there are three modes of heat transfer, right? What are those modes of heat transfer? Conduction, convection, radiation. I did talk a little bit about that. I won't spend to what is it? This is a long class, another 45 minutes left. Okay, time to time I'll be a little slow, giving some time to relax. Okay, otherwise I'm gonna lose you. Okay, I know that. Okay, so what are the three forms of heat transfer? Conduction, convection, and radiation, right? So what is conduction? Conduction deals with solid. What is convection? Convection deals with
Air.
Fluid.
air, fluid. I heard both. Both are correct, but if I'd like to say fluid, that is more correct because it not only deals with air, it deals with any kind of liquid as well. So fluid, right? So convection deals with fluid. What about radiation? Radiation deals with solid or fluid?
It's both. It can radiate through space, so I guess it could do either.
It can deal with the fluid for sure, but it can usually usually it can deal with the solid transparent way. It can in different aspect, view factor complex thing, we're gonna understand it at some time. But for now, just understand radiation doesn't care about any medium. The medium is bad for radiation. Okay? The radiation doesn't need the medium. As I said before, just like think this way, we're getting the sun energy to Earth without any medium, right?
Yeah.
Initially, long ago, scientists had an idea about ether. Later, it proved it's wrong. There is nothing.
Idea about what?
Ether. There is a term called ether.
Oh.
Yeah. So that was a scientific assumptions, a hypothetical thing they were thinking in between the sun and Earth in the space. There's none in this space. There's nothing in this space. Okay. Now it's think that way. Okay. It was think that way before. Bottom line, we are getting sun energy because there is nothing in between sun and Earth. That's why we're getting most out of it. Okay. We do have the atmospheric layer. That's why by the time it comes to atmospheric ground level, we are getting much less, which is good, and that's how it get balanced. If you believe in God, God balanced everything for us. Okay. If not, nature balanced everything for us. Okay. Either way you wanna think. So bottom line, we are in a perfect harmony. Okay. In the Earth. Otherwise, we couldn't live. It is impossible. So the more you think, more you understand, the more you're gonna go in depth on those. Okay. All right. So what I was talking. Radiation. You understand? Radiation doesn't need medium. So now the question is, I say like I have high temperature, here is lower temperature. I'm constantly giving away heat, right, to air or these other objects, right? How it happens is radiation. One of the medium, convection could be there, like air and me has a dynamics happen in terms of convection. But radiation, let's focus on that. So what happened? So like I'm giving away heat to this surface, which actually is happening by the way. Okay, because I have 98, this one is 70. Okay, so I'm giving away heat from me to here, minuscule of it, but it still is going there. Okay, you have to understand that. Okay, so I'm giving away heat from here to here. What is air is doing here? Air is actually resisting the radiation heat from going from me to that surface. Is it clear to everyone? Air is blocking actually. Now, how much it's blocking? Probably percentage of 0.00 something percent. It's negligible again, but it's doing some blockage. Makes sense? Instead of air, if I could be inside a, say like this is a swimming pool that is at the bottom of the swimming pool. I'm at the bottom of the swimming pool, right? It's all water. Then the blockage of radiation could be even more because water is much dense. Does it make sense? Air could have do the less blockage of the radiation from me to here, but it still is there. Okay. So to give an example, say like if we are in this classroom with like only five, how many, 7 or 8, we are now here, right? Think this way: you have 100 people here. What would you feel? It's starting to feel warm, right? So there are two way we are all thinking. We have 98, right? Yeah, has 70. So the air temperature will goes up definitely, right? So not only the air temperature, pretty much everything's temperature is going to go up, but we're going to feel the air temperature goes up much more faster way, right? Because air absorb more of the heat. Okay, I was just trying to tell you here, we are constantly radiating heat, okay, and we can only feel when more people are here. We are not feeling it now because just only one person is here. Okay, is it clear? Radiation is a very in-depth concept. We're going to learn the equations. We're going to apply these equations in math problem. Then we'll have much more better feeling on that. Okay. For now, there's the overview. Okay, three medium of heat transfer. I was talking: conduction, convection, radiation. Right. Now I'm gonna just put a little bit more on the notes here. So conduction. Let's start with that. You wanna start to take the note because this is so important. Start to take the class notes. Okay, so on conduction, you see, you have heat is going from one side to another side. Okay, you have these two different temperature T1 and T2 in these two side of the wall, right? What is that I draw here? This is considered this is a window glass, or this wall from inside to outside, or this wall from this room to that room, just any wall, right? Obviously there are two different temperatures in two different walls. You have this T1 and T2, right?
And then then the and then the heat rate Q, this is the heat rate, right? I was saying about that, which is the unit of watt. Remember that is passing through that one side of the wall to another side of the wall. Now you need to know what is the area of that one side or the other side of the wall. If both the area are same, assume that's the area of that wall, right? So area of the wall is this is L, this is W, so L multiplied W, right? Please understand the hatchet line of the area of the wall. All right, so then the heat flux, everybody remember the heat flux? That's Q prime, Q double prime. That's they call heat flux. Okay, then heat flux can be related with the heat rate Q by this equation, Q divided by A. Okay, so you can also write Q equal Q double prime A. Now that you know what is Q double prime, what is A, you know everything, right? Unit wise, if you'd like to know a little bit more, heat flux as a unit and SI system is watt per meter square. Heat rate is a unit on SI system is watt. Area has a unit in SI system is meter square. Okay. All right. Now you'd like to know a little bit more with this Q, right? That's the relationship with Q prime A and Q, right? So this Q heat rate, I won't be writing this Q anymore, right? You understand what is Q now? It is the heat rate. Okay, so Q can be written as Ka dt minus dt by dx, and there's a negative. So that's the actual equation for conduction. What we are doing now, conduction, right? You see the title, conduction. So my goal would be today to give you intro as well as those basic equations for conduction, and radiation, right? The one that you'll be using all the time. Most likely after today's class, you should be able to start to understand the homework problem or the example problem in the book, okay? But try to understand this equation that I wrote, the last one, Q equal to minus Ka dt dx. If it's bothering you, it's not too clear, maybe you guys can even come further on this
So
side.
that side's okay. The lights are a little too bright for me to read the left side.
Okay, let's take care of that line. You let me know when I turn off the light.
Sure, thank you.
Any light?
That's better, yep.
It's a lot better, yeah.
All right. So you obviously seeing me writing a equation which has some term that you are not familiar with. K. You guys are familiar with K? Did I explain K and thermal? Maybe not. K they call thermal conductivity. You heard about that term before, thermal conductivity. Okay. Conductivity has something to do with conduction. Okay. The name goes with that. Conductivity, conduction. Where it happens? In solid or in fluid? Conduction happening solid, but conduction can happen in fluid as well. Just let's not focus on that aspect, okay? For now, just focus conduction happen only on solid, okay? That's advanced topic. Conduction can happen for now. For your purpose, you're in a fundamental stage, right? Initial stage of heat transfer. You would be always understand conduction in solid, convection in fluid, radiation doesn't need any media, okay? You understand that, okay? That way. So the conduction I was talking about that. The equation that I had here. Q equal to minus K. Let's talk about the minus a little bit later. Minus K A dt over dx. So the K is the conductivity, right? I told you that, right? What is the unit for the conductivity? Watt per meter Kelvin. Okay. We're gonna focus on conductivity a lot because this is the property you have to find it from appendix all the time. Okay. Move on to area A. Now do you really understand the area A? That's the question. When the conduction happens from one side of the wall is the best example or easiest example to understand. When the conduction happens from one side of the wall to the other side of the wall, right? Then what area to account here? Is this the area of this side of the wall? Is this the area of the other side of the wall? Is this the area of the cross section of the wall? What area do you think is important here?
The face area, face.
The face area, the area where the heat is actually going, right? If it is going from here to there, here to the other side of the wall, it is not going to go to a single point. It is going to go through all the wall side, right? Is it clear? The same thing is true here. All the wall. So that face area, always remember that. So the sketch that I had here, okay, it says T1 and T2 temperature. What are those two temperatures that are referring to which side of the wall? One is the inside of the wall, another is the outside of the wall. When you're talking about the area, what is the area that we're talking? Not the cross section that you're seeing here, rather the whole hatched area. Does it make sense? Or in other words, this whole area. So you have a good idea about the area now. The K I said I'm going to talk more about it, right? Conductivity and dTdx is something that you should know, right? From Calc 1 or Calc 2. You guys know, like this is a derivative, right? Change of temperature with respect to x. What is x? X is the distance, right? What distance is talking about? Across the wall. So it's along the thickness of the wall. See, it's a little complex to understand. Why I'm saying that? You have the area which has this hatched line. You have the dx here, which has nothing to do with the hatched line, which has to do with the thickness of the wall. You understand why? Because the temperature change happens along the thickness of the wall. Inside the wall, outside the wall, two different temperatures, right? Remember that? So along the thickness, is it clear, everyone? So why this dx that I have here in the equation is different than the A? The area A is for the face, right? Everyone see that? And the dx is where? Is the thickness, right? As if like you are walking across the wall, right? You're penetrating the wall. So that's the x. And what is that delta T? Obviously, you know the two temperatures inside and outside are completely different. There is a change of temperature, okay? So that's the delta T. Now you understand the equation? The conduction equation, everybody understand it? Okay. So this, why I have this dt dx, in oftentimes you would be seeing instead of dt dx, they have this del t del x. Why I have this dt dx? So that's really important to understand why I have this dt dx. What do you think? Any idea? Why I have this dt dx?
I don't understand why. I don't know why it would be a derivative.
There's a derivative and there is this simple change of temperature. There's two different things, and both equations are for heat conduction, right? So obviously the bottom one that I have is a special case. Does it make sense? The top one that I have is the generic one. That means dt dx. You guys remember the slope equation, the derivative, the slope equation dy dx, right? So the slope usually for a line is for any individual point, right? You remember, if you have a zigzag line, any individual point does have the derivative, right? Now, inside to outside of the wall, if we assume, the special case now I'm talking, if we assume the heat is transferring uniformly, mark my word, uniformly. If the heat transfer is happening uniformly, means the material inside is very uniform, right? And there is no heat generation inside the wall, nothing. It's a plain simple wall, right? Then the special case will be applied. Is it clear? dt dx. But the generic one covers any and every case in conduction. Means, say like from this side of the wall, right, Mitch, to the other side of the wall, the material inconsistencies are there. So heat won't be passing it, in a homogeneous way. It will have all heterogeneous heat transfer. So the temperature will be all over the places, right? Does it make sense? In that case, the heat rate that I was talking is completely different at every point from here to outside. Does it make sense? And that's the generic case. It can happen, right? You may have multiple layers in the wall, right? It may not be a straightforward case. So what to do in that case? So for that reason, the DTDX is important. The question is, are you using the DTDX and actually solving it? Like DTDX, the derivative? Yes. Remember, I was saying in the last class, like the first half of the semester, you have to deal with the differential equations. And sometime, actually, most of the time, you're gonna solve this derivative DTDX. Maybe you'll be given with the temperature equation, right? And then you have to solve the DTDX from the temperature equation, and you have to plug it to find the heat rate. Understand? But initially, for class homework problem, you don't possibly have to do that. You just simply use this special case. Okay? I'll talk more about it. Yes.
Is there a way to average the K factors?
Average the K?
Of the different materials throughout a wall to like simplify it?
Yes. So here's the thing, like the change of temperature for different material will gonna act completely differently.
Yeah.
So when you're gonna deal with that Q, the heat rate for that particular material, you can find it. You can find the all others. But the interesting part here is the heat rate would be same for all the materials. Now, because those materials are different, that's why the temperature gradient is going to be different at different material. But the Q would be same. Why? It's so important to understand as well. Heat rate would be same.
Steady state?
In a steady state, heat rate would be same. Say like some amount of water is going from here to outside. And it would be same for no matter how many layers of the material here on this wall. Does it make sense? And this is a little bit complex. We'll understand it slowly, okay? But bottom line, this Q prime, when it is penetrating, just like like flood of water is going through, no matter it's passing through a hill or a straight line or whatever, the flow rate is always same. No matter if you have a small fly, the flow rate is same. The velocity and the other thing get a change, but the steady flow rate is same. That's the same thing. Understand? And that's advanced. I don't expect you to understand that now, but I just explained. Multiple layers, different. That is advanced. We're gonna understand it after a few weeks, okay? For now, just understand special case DTDX. Sorry, del T, del X is special case. DTDX is the generic, okay? And the K I was saying I'll talk more about it, right? Let's talk more about it. So the K is called what? Everyone wanna take the class note. K is called what?
Conductivity.
All right. So thermal conductivity. Anybody remember the unit that I said? Let's see. No, it's all right. Let's see if you can figure it out from the equation itself. So you guys remember the unit of heat rate is W, means what? The unit of area is what? Meter square. The unit of temperature is what? Kelvin. The unit of del X, right? By the way, I didn't quite clarify the del X, right? This is the X direction, right? And in this particular case, this is the del X, right? Everybody got it? Everybody got the del X and A, right? Is it clear? Take a look on the sketch and see if it doesn't make sense. Not, I'll explain it again. Is the del X is clear? All right, if that's the case, so tell me what would be the unit of K?
Would be watts per Kelvin. Oh no, it would be just watts.
So I have two different answers. Watt per Kelvin. I have. Let's do what is not the answer, obviously, for K. So how many of you are with the first one? How many of you are for the second one? Okay. I would go with the first one. The reason is, let me explain why. You see, this Q has a unit of watt, right? The K, I'm gonna just write K as K, and then A is meter square, right? And this Kelvin here and meter here. So this meter and meter square is gonna cancel out. So the K, oh, by the way, don't get confused with this K and this K. Usually the way they write the conductivity K is small k and the unit Kelvin K is capital K. Okay, that's how they usually write, okay? But it really doesn't matter. One is the unit, one is the symbol, right? So this K unit is become watt per meter Kelvin. Everybody got it? Okay, so now these are all the rough thing. I don't want to keep it. This is for understanding only, okay? So that's the unit for K. K is conductivity. I'll just take it away as well. So the unit for K is watt per meter Kelvin. Now you're going to remember it all the time, right? Because there is the other thing that you often have to face, which is called heat coefficient. That's for convection. That's the next thing that I'll be covering. But I'd like to pause here a little bit just to see like if you understand everything about the conduction. One thing I didn't quite clarify yet. Why there's a negative heat? Do you expect heat is going to flow lower temperature to high temperature or high temperature to low temperature? High to low. So that del T, right? When you are doing the del T usually means what? T2 minus T1. As if like the lower temperature minus the higher temperature. Is it clear to everyone? So to get the heat rate in positive, right, we're going to put a negative. So that negative will take care of that lower to higher thing that I just mentioned. Is it clear? You got to think a little bit on that. Okay, why this negative? Again, heat flows high to low, right? So high is T1, low is T2. So you will be getting what? T2 minus T1 negative value. So that negative and negative become positive. That's why. So that's about the negative. Like everybody gets confused with that heat rate equation with the negative. Okay, they get confused. I got confused when I was undergrad. Okay, why there's a negative? Okay, it bothers me all the time. Okay, now it will not going to bother you, right? There's this is the reason there is a negative here. Okay, now you guys are ready for the. I really would like to use as much time as possible, right? So much to cover, so much interesting stuff to cover, right? So let's start with the convection. Ready? I need some time. Ready, right? Convection. So convection it is. Convection. Convection has the equation again, heat rate Q, HA del T. Now I'm saying like HA del T, all sorts of things. Now I gotta give you some example, right? Where does usually the convection happen? In a solid or in a fluid? Air is a fluid or not? Air is a fluid, right? So like air is moving on the top of a plate. The plate temperature is Ts, and the air temperature T infinity. Oh, by the way, you'd be seeing me writing T infinity all the time for air temperature. Okay. So what I was saying, like the Ts and T infinity. Now, the T infinity could be higher. To give an example, say like you're dealing with the oven and baking a cake. Your cake is here, the surface Ts, and the air temperature inside the oven is T infinity. Okay. The other case, other scenario that I can give it to you, like you see in a summer, okay, outside wall get exposed with hot air blowing during the summer in Texas. So the outside wall is going to get heated, right, because of the high temperature of air. So it can go either way. Give you two extreme example, right? So this Ts assume is higher than T infinity. In that case, this del T would be written as HA Ts minus T infinity, and that's my Q. Now here's the thing: people oftentimes use a subscript for Q for convection, okay, and Q for conduction. You can change it. That's the way people use. COND means conduction. CONV, capital V. Sorry, not capital V. V, Victor V for convection. Okay. Everything's good. So the convection is very straightforward and very easy. So after midterm, we'll be dealing with convection only. Okay. Is it so easy as Not really, but it's much easier than the conduction. What will be doing there? I will be doing only this equation, a simple equation that you probably learning in high school physics. We'll be using that equation all the time, but that h that you are seeing here, they call convection coefficient. Okay, we'll be learning very complex equation to find the value of h. But at least it's algebra, it's not differential equation. Algebra you can deal with that, right? It looks very scary, complex equation. You just need to know how to find different parameters on that equation, right? You just need to know a little bit of the fluid mechanics background, like Reynolds number. You remember the Reynolds number, Prandtl number. I don't know if you learned Prandtl number. For sure, you will remember the Reynolds number, right? From fluid class, Reynolds number, ring a bell. So we'll be using that whether to figure it out. Is a turbulent flow or it's a laminar flow or it's in transition. Based on that, the H equation will vary. Okay, there are a few more numbers are going to come in play. They call Nusselt number. You heard about it? Nusselt number. There is this other number going to come called Prandtl number. Now I did talk about three numbers. Now let's focus on the Reynolds number. Okay, so the Reynolds number is it a what's the unit of Reynolds number? It's a unit.
Unitless.
It's a unitless. Thank you. It's a unitless because it's a number. If the name itself says it's a number, it's unitless. It's called dimensionless number. Okay, what is that called? Dimensionless. It doesn't have any dimension. So the Reynolds number definition does have four parameters. If you remember that, the velocity, the diameter or the length, whatever, then density, then viscosity. You remember those four terms? Okay, so you put those terms such a way in a relationship, so all the units goes out, right? So it's become a dimensionless number. Why emphasis on the dimensionless number? Because you see the Nusselt number and Prandtl number, which I'm not going to give you the equation now, not in fast class for sure. Okay, those two numbers are also dimensionless, and from after the midterm to the end of the semester, you'll be dealing with even not from the midterm, before even the midterm. When we'll deal with the conduction, transient conduction, we'll be dealing with a Fourier number, other numbers, right? For transient conduction. Bottom line, the dimensionless number will gonna play a big role in your heat transfer class. Okay, some of the numbers that I talked about now: Reynolds number, Prandtl number, Nusselt number, Fourier number, right? Biot number. Those are the numbers you'll be seeing all through the semester, okay? And all of them are dimensionless, and all of them you will be using, especially for convection. Now, again, let's now focus a little bit more after the number with the H itself, right? What is that H they call? You heard about the H before, the naming of the H? No. It's called convection coefficient. So there are different names, different places, different book used. But at the end, there must be a coefficient. Okay, so I'd like to be generic. As an example, say like you see the heat rate that we are using Q as a watt, right? In Cropper, I use heat transfer rate. Sanjay use heat rate. Okay, so it's depending on the author would like to use what way. But as long as you're seeing a rate, means per unit time, that you know what you're talking, right? The heat transfer rate or heat rate. The same thing is for H. As long as you're seeing the coefficient at the end, that you're talking about H. Is it clear to everyone? So okay, what are the different names out there? It could be heat transfer coefficient, it could be heat coefficient. I mean, there could be more. I know those two for sure, right? It could be it could be convection coefficient, and people use different name. I mean, as long as there is a coefficient, they're talking about this H, and you gotta understand it has something to do with convection. Okay, K has something to do with convection or conduction. Conduction.
Oh, okay.
K.
Okay.
It's a trick question. I mix it up immediately. So H is convection, K is conduction. Okay. And radiation, some few more terms we're gonna come. We're gonna learn even today. We have time. We're gonna learn today, right? There is this emissivity. Heard about the term emissivity? Emissivity. I don't know how I'm pronouncing it. Correct or wrong? Emissivity. People use it. EMISSIVITY. Emissivity. Did heard about that thing? Everyone might have seen the IR gun, right? IR, not the gun. IR, temperature gun I'm talking, right? During COVID, it was a popular thing. They just,
get the temperature by doing some measurement by IR fan. Anyway, so IR, when you are using it, you will be seeing on the top it was written somewhere that emissivity of the IR that they were using on the equipment. Okay, the emissivity level. So as long as the temperature measurement happened on that media on that emissivity, then you will be getting the correct temperature. Okay, by using the IR gun. Okay, advanced topic. Don't expect you to understand it now. So radiation topics we are talking, right? So emissivity is one of the topics. Okay. The other topic is in radiation called sigma. Actually, I'm done with convection. That's why I'm moving slowly to the radiation. You understand it, right? There's just one small thing for me to finish on the convection, just to write what is H and the unit of the H, and there is not that much to discuss on convection, right? You understand? If you want to go me a little bit detail, I can go. Like, convection can happen different way, like naturally or forced, right? I did talk about it in last class. I don't have anything on notes here for that. That's why I'm speaking. Okay. Basically, force means you have a forced air by control media by fan or something blower. Okay. And natural means due to density gradient, the heat transfer happens. You guys know, like, when the temperature change, the density of the air or any material per se change. Density is a property of temperature. You guys know that, right? The more the temperature, higher the density or lower the density. Lower, obviously lower, right? Like in honey in winter, it's like very thick, very dense, right? In winter, it's like fluidy. So higher temperature in summer and lower temperature in winter. Yeah, it tells you everyday life, right? High temperature, more the density, low temperature. Sorry, high temperature, less the density, more temperature. What I'm saying, less temperature, higher density. Opposite, okay? All right, coming back to this H thing, right? So I was talking about I was talking about this H and Prandtl number equation. Let me finish that, and I'll just shortly. I'm gonna go to. I'm gonna go to the radiation. Okay. So this H. Everybody take the notes, please. So this H is called convection. Let me write it this way: convection coefficient. Okay, and I was talking about forced. Oh, the unit. Let's see if you have some idea about the unit. Okay, let's see if you can figure it out. So this is what the area unit is meter square, right? The change of temperature unit is Kelvin. Can anyone tell me what would be the unit for the H or convection coefficient? Just like before. Watt per meter square. In this case, it would be meter square. Take a look here. You are trying to find the unit for H, right? So then you have this Q and A and del T at the bottom, right? So the Q is what? A is meter square, del T is Kelvin. You will see that? Take the notes, because if I'm gonna see you messing up with the units, that means I'll have understanding. You don't understand it properly, okay? Please make sure you know what is the unit of the H, what is H means for, right? Okay, and the three dimensionless number that I was talking is the Reynolds number, RE, Nusselt number, and U, right? Prandtl number, PR. So these are the number we'll be using in convection heavily, okay? And the other two numbers that I was talking about is Biot number. That goes with conduction. Just 1 second. Biot number, PI. Now, I don't want to go any further on first class for sure, but you may want to take the notes for those, whatever I wrote here for convection. Okay? That's the equation. Now, I was just saying, like, complex algebraic equation will be given to you after midterm for the H value, right? Involving with Nusselt number, Prandtl number, Reynolds number, right? And in different scenarios, you'll be seeing different equations. Remember the force and free convection I was talking? Force and natural convection, right? Force means like some blower, fan, or blah blah. So then you have one set of equation. If you have like natural convection due to density gradient, any example I was giving,
the different sorts of equation, right? So those complex equations, really, really big equation, you'll be solving them to find the value of the h. Okay, but for now, let's say like let's say like for first homework problems, you'll be seeing still gonna find the Q convection. In that case, you'll be given with the value of the h. You don't have to use any of the equation because you're not ready for that yet, right? So initially, you'll be using this simple equation. We just need to know what is Q, what is H, what is A, what is this del T that we are talking. Del T, you guys have a clear idea now, right? The change of temperature, it could be high to low, means like, it can vary, right? The surface to air or other fluid, whatever. Okay. The convection is clear to everyone? I started with radiation a little bit, so I'm going to start writing radiation now. If you're good, then I should move. Remove. And you'll be seeing most of the things in the next few slides I've already covered. Even though you're seeing me staying in the number 3 slides for more than 1 hour, but actually I covered almost everything. Okay. Okay. I'll just point it out shortly. All right. So the next thing would be, as you can see here, right? Okay. As you can see here, did I cover all of them? Did you see that all the slides are covered already? Harley, you're seeing it, right? All the slides are covered, right? Everything is covered already, right? So now we are in this slide actually, radiation. Okay. Okay, and our goal is to cover up to this point, okay? So it'll be done with the whole slide for the first module, okay? So that's our goal. So next class we can do some problem and we can possibly deal with the first homework easy, okay? So what did we learn? I mean, I have still like 7 minutes, it's fine. Next 5 minutes I can finish the radiation. What did we learn so far? Anyone would like to volunteer? Convection, for sure we learned. What else? Coefficient, yeah, coefficient, convection coefficient. Conductivity. Those two equations heavily. What else you learned? Equations for Q. Equations for Q. Anything else? What about the units? Did you learn some units for some of the parameters, important parameters? Did you learn something about heat transfer, heat rate, heat energy, thermal energy, all sorts of things, right? Did you learn all of this at the beginning? Okay. What else? We learned the detail of conduction, right? Like this direction of X, what does it mean? In thickness, thickness, very good. Thickness direction. We learned the surface area where we'll be looking, right? We learned when the heat transfer really happened. We learned the negative impact on the equation, why this negative is there, right? Now we are ready for the. We also learned some dimensional parameters, right? Today, everybody learned it, right? Now what are you gonna do? What do you want to do now? When you go home, you'll forget. You'll come back again for next class. Waiting. No. If you do that, you can't remember what happened in this class because the first time you are most of the thing first time you are hearing, right? So I mean, hearing is really good, visual is good, writing is good, everything is good. But for you to absorb that, you got to read. Everybody is going to read chapter 1. Please do so, okay, for your own benefit. Otherwise, you're going to forget. To get attached to this subject, I want everyone to get attached to the subject. Do the homeworks by yourself. Don't try to look for solution manual here and there. These are possible problems. No matter whatever I give you the problems, if you have a bad intention, you're going to get it from AI or somebody else, okay? It doesn't really matter. If the homework is from last year or whatever, your goal should be not for look for the solution. What are you going to do? You're going to do it by yourself, with your friend, and getting the help from me. If I don't have enough time, I'm going to give you a tutor, right? I do have time. Okay? I have a small number of students. I can manage some time, right? So your goal should be: don't worry about the answer. Do whatever. I mean, last semester, I found Matt used to do like he doesn't care about the answer. He just put everything. Did I give you a good point? Like in the thermo homework, you did care about the answer. You tried your best. I like that approach. That's what I was saying. Like. No, you are not in. You are in good shape. So I'm just saying, like when I was grading the paper, I noticed those. I mean, when Steve took my class, I mean, I remember he was going really advanced stuff, right? not even required. I mean, everybody else did very good job. I don't want to point out anybody's name. I just trying to give two examples, right? David used to give like this much big homework, right? So hardly I never missed any homework. Mitch always punctual in class. So everybody has their good qualities, right? So I've been doing classes with you for a long time, and I've been expecting you to do the homework by yourself. Okay, max thing you can do with your friends. Okay, and just talk with me if you have any issue. But don't ever try to, because as I said, like sometimes some instructor try to change the portions from different years to different year. I try not to do that. Sometimes I give different. Nowadays for AI, whatever I give, like they can get it, right? If you want to get like solution, you can get it, but that won't help you to learn stuff. We're running out of time. I mean, radiation, I'd like to go really slow, but just don't go still. I mean, I'm not going to write anything, but let me speak a little bit, like 2 minutes about the radiation. So you'll have a complete idea for today's class, right? What is radiation then? Okay, I did talk about the radiation. Like now, the equation was I'd like to show it to you. I'm not going to write as I said, but I'd like to show it to you, right? And I'd like to talk a little bit more about this equation. Okay, so there's these two equation. I'd like to show you this one. This one is really important. What you're seeing here is surface. Okay, try to understand what you're seeing here is surface, right? Red surface, and you're seeing a dome. Okay, think this red surface is this surface, right? And the dome is this wall, means ceiling wall, this side walls, everything, right? That's the dome. You understand that? All right, so now this surface no temperature different. Resume. This surface has some different temperature. Say like you have a hot plate. You see that hot plate? That could be a perfect example. I connect that hot plate, right? I connect the hot plate, and after a while, the hot plate temperature is really high, say like 120 degrees Fahrenheit. What is the ceiling temperature? 70 to 75. We don't know. We have to calculate, but it could be somewhere in that range, right? So that's the equation to calculate how much of the radiation exchange happened from the hot plate to that surface. You see that equation? We got it? Okay, so now try to understand a little bit more about the parameters on that equation. Okay, so you're seeing here this epsilon. Everybody is familiar with the Greek letter, they call epsilon. Okay, epsilon is emissivity. I'm not going to write, I'm going to do it at the first thing next class. This is sigma. You guys know about sigma? That's they call Stephen Boltzmann constant. What is that? I talked to two scientists named Stephen Boltzmann. Those two scientists together invent this radiation phenomena, and there are other scientists as well, But those two are named with this sigma, okay, and this sigma is a constant. Okay, the value of the sigma is 5.67 10 to the power minus 8 watt per meter to the power 4 Kelvin. The meter square Kelvin to the power 4. Sorry. Okay. Again, I'm just giving you the values. Next class formally I'll approach it. So that's the sigma, right? What else you're seeing here? The surface, this hot plate surface temperature, and the surroundings. SU1 means surroundings. What surrounding we're talking? The dome in that case. What is our dome here? This everything around it, right? So you have now a little bit of idea about the parameters of the equation, right? We're running out of time. I'd like to just introduce you that. Okay, so in next class we start from somewhere where we have already had some idea. Okay. Any question with today's class? You see all the materials are right already there for you in right space, right? You've noticed here, right? And as I said, if you miss any class, let me know. Or if you are struggling with any class, let me know. We'll try to get a printout, physical printout. I can give it to you. Okay, that way we can be safe. Okay, in this situation here. All right. Have a good weekend. I won't be seeing. I probably see you, some of you, in my other class, but I won't be seeing most of you.
Oh yeah. So I'll change it. Yeah. I need to rewrite this anyway, because these are rough, and I gotta stick with it next time. Thursday. Probably read the text tomorrow. I need to find the book today. Because what do we find? We found the one for ethics.
Yep.
We haven't found one for
Should we wait till Friday to accommodate a presentation? I've received the
Yeah, you do the statistics I do tomorrow.
I'm gonna read the ethics.
When's it due?
Friday.
Tomorrow? In
In
class?
statistics is
Is it a physical copy in class? Or?
I have a request for you guys. Please don't miss any class, okay? Yeah, if anybody missed the class, the reason I don't like it, it's very hard for me to, catch up on the
This
materials.
semester I should be able to give you forewarning for any missed class.
Yes,
If
yes,
I had
please.
to miss one,